And Nancy, the floor is yours.
Okay. Hi, everyone. I'm Nancy, and I'll be giving a presentation on the vulnerability of deep reinforcement learning agents to policy manipulations. So in the trading domain has recently been thinking of how to automate trading, right? So it's being done through machine learning, a particular type of algorithm that's being used in machine trading for automation of trading, right, would be through reinforcement learning, and specifically deep reinforcement learning. Now, why would necessarily traders be interested in deep reinforcement learning over the latter of reinforcement learning? Well, we can see here that reinforcement learning, right, it provides a stochastic control process, which you can mathematically set up the task under a framework that can have an agent, given some state, can produce some action. And neural networks are some sort of way to get around the idea that data can be extremely high dimensional, so that it's really good with feature engineering high dimensional data to an action or to some key values that we want. And neural networks are known for being very generalizable. But unfortunately, there are problems that come along with neural networks. I'll get to that after that. This is the basic framework of how an agent interacts with its environment. An agent, given some state, maybe for trading, there's a tuple of values like the high, low, and close price of a particular stock or a currency. And then from seeing that state, it produces an action. Then the environment returns an observation, which is the next state, and a reward for the action that is taken at that time step. This reward can be a simple profit return if it's selling, but this may also be a different type of reward, like some other ratio, like a Sharpe ratio, which isn't necessarily tied to immediate profits. So if we can see down here, we are considering Q learning, and Q, as you guys might not know, but Q learning is a reinforcement learning algorithm that's used to calculate, to obtain optimal Q values, usually which are tabular, but in this case, right, we are using deep Q learning, so it's replacing with a neural network. And from those Q values, you can extract an optimal policy. But the problems with neural networks is that we know that they are susceptible to adversarial attacks. And some examples of adversarial attacks are these white box optimization attacks, which was one of them is called fast gradient sign method, and the other one is proposed by two authors, Carlini and Wagner. But ultimately, what you can see here is that by perturbing an input just slightly in values, that the action that comes out or the classification that comes out is misclassified. So what does it look like for a trading DRL agent, right? If you can see over here, that the observation space for at least the trading agents, deep reinforcement agents that we are looking at, its state space is a tuple of values, a tuple of n time step values of its relative high, relative low, and relative close price to their open price for one of them, for one of the agents that we're using. And what we are doing is we're perturbing one tuple, which is the earliest or the most recent tuple in this history, to manipulate the action that comes out of this agent to be different from the true input. So if we can see over here on this right of this table, here's an example. I pulled up these DQ, and these are samples for successful attacks for non-target FGSM on one type of DQN that we were using. Just to emphasize that these adversarial attacks are extremely close in value to their original counterpart, value X, but their actions are different. So if we can take a look at the third line down, we can see that we have a value that's really small, a value that's negative, and then a value that's the same value as the first. So this dynamic, you can see that it's going to be the relative high, relative low, and relative close. Now, its adversary counterpart that we exchange this tuple for follows the same dynamic, but the action is different. So the original action was to wait, which is 0, and then the adversarial action that it took, the action that was taken instead by interchanging this perturbed tuple of values, is action 1, which is to buy. So normally, for deployment of these agents in the wild, in the idea that you're going to be using them for actual monetary purposes, right? It is important to consider adversarial attacks and threats that exist for this model. So you can see that over here on the right, we have a basic diagram of a deep reinforcement learning agent, and for specifically trading, of where it pulls data from. So we have some input channels. It creates this state vector. And then between the state vector and the reinforcement learning agent, right, we can insert some attacks where we either intercept data from the state space and exchange it out for like what we did before with some perturb tuples, minute perturb tuples, or we can do some other attacks, particularly at test time, which can change the trajectory of the agent's action. Yeah, you can see some other channels that are like that can also be perturbed or can also be attacked, but they aren't necessarily easy to reach. The original framework that was used for this, for the general DRL agents, not specific to trading, is proposed by Bezadan. So yeah, we have a more specific model for trading. I wanted to introduce some definitions that are important to understanding what kind of attacks these are. I call them flavors because they can be multiple properties. So we have targeted and non-targeted attacks. Non-targeted attacks are attacks when an agent takes an action other than the optimal action at a time step. Target attack is when an agent takes an adversarial action. So this is a specified action by the adversary instead of optimal action at a time step. There are white box and black box attacks. White box attacks are attacks that are implemented because an adversary has enough adversarial knowledge of the target to craft adversarial attacks. Black box is the latter, where we do not have enough information of the target agent, but we have some sort of direct or indirect accessibility to the agent. There are active and passive attacks. Active attacks are attacks that are intending to change an agent's trajectory. So specifically change an agent's action at a particular time step or at any time step. And passive is where we intend to gather information about the target agent. So not necessarily interfere with its policy or the trajectory of the agent. There are test time and train times attacks. Test time attacks are what we're going to be focusing on in this paper, is when we attack an agent that's using a fixed learned policy. And train time attacks is an attack on an agent during its training phase. So I'm going to give you a little bit of an idea of what these environments are like. We have two environments. We have a basic environment where it's directly built and leverages OpenAI Gym, and its action space is relatively simple. So it has wait, buy, and sell. It only has a single share that it can buy or sell for this environment. The reward function is the simple profit or loss from selling the position, and the observation state for what we are perturbing is the relative high, relative low, and relative close prices. For the TensorTrade environment, TensorTrade is an open source framework for trading reinforcement learning that also leverages OpenAI Gym. It's just a little bit more complex. It's community supported. So the action space, it can be customizable. It has a managed risk scheme that has a default setting. So the action space is relatively more complicated. It's a product of one particular action, which is wait, and then the rest is a product of the take, stops, and trade sides and buy and sell actions. So this action space can scale depending on how complicated or how you want to manage these risks. Then the reward function, they have a reward function called the Sharpe ratio. It uses the Sharpe ratio, so it's not necessarily tied directly to the external component or securities like a bank, like from the image before. It's not necessarily tied to that, but it is dependent on the excessive return, expected return minus the risk-free return over the standard deviation of excessive return. We have in our targeted tuple in this observation state that we're targeting is a tuple of also 3 values, which two are which are called technical indicators. The MACD and the RSI are technical indicators for humans that use to estimate whether or not it is good to buy, sell, or trade stocks, you know. And we have one particular one that was defined, but this was defined for the default. So we just used it as part of the default setup. Also, TensorTrade includes additional components to the environment that are a little more similar to real life, to the real life environment. It has an ability to have a portfolio, and the agent has a net worth. So these are external components or securities that are tied to the agent. And in real life, that's necessarily the case, right? So we implemented one type of attack, which is called an observational delay attack. So this kind of attack is an attack on the observation channel. It is when we delay an observation at time t to be seen at a future time step t+1. We decided to use a time step of 1 because it is both the minimum amount of delay and, well, that's basically it, right? We want to test the minimum amount of observational delay, perturbation, or interference as possible to estimate the impact, the minimum impact of what could happen to the agent. And as you can see on this page here, if you test both agents are necessarily impacted by a one-time step observational delay. Now, the importance of this kind of attack is that this attack isn't crafted. This attack is actually quite inexpensive to execute and use, because you don't actually have to craft a tuple of values. All you have to do is have the interception be the man in the middle attack, like intercept it for a different time step. And this kind of attack depends on the locality that time series data will kind of mask the anomalies that occur from one time step to another, because they're not necessarily very different from one time step to another. So now I'm gonna have to get a little bit mathy, but it's not necessarily too important to explain exactly what's going on. But for non-target attacks, right, we have FGSM and CW as mentioned before. For SGSM, right, we are going to calculate the gradients. We're going to calculate a gradients such that if it's a non-target attack, what particular it's going to point to the gradients in respect to the image, or not the image, but to the input data, such that is pointing in the opposite direction of the minimum of the target label, of the true label. And then you clip that, you pass it through the sine function, so it clips it between the values of 0 and 1, so that this is for normalized data, it is the extreme limits of how far you can perturb the values. And then you apply an allowable perturbation of this, so an epsilon that's bounded between 0 and 1, to this maximum perturbation in all dimensions. And then you add it to, or you apply it to the original image. So you're starting from an image, and then you apply this perturbation, and it's slightly off from the image and from all dimensions. So it's a uniformal step size in all dimensions. For the basic DQN, you can apply this directly, and you don't have to interfere too much, because the relative closing price, high price, and low price are all around the same sorts of ranges of values. And if you take a step size in any of those dimensions, they're not odd to see that they can be uniform across all dimensions, relatively speaking. But for TensorTrade, that's not the case, because as Ben mentioned before, it's using a set of 2 technical indicators and 1 other feature, which are not of uniformal, differences in values. It's non-normalized. If it's normalized, they would be, but in this case, it was not. The reason why we would decide not to normalize it in this case is because we can preserve some of the human readability of these adversarial images, adversarial samples that we are making. So what we can do instead to compensate for this is that we can apply an external set of vectors, let's call them scalar vectors, right? Which will scale down these values so that they match the distribution, the true distribution underlying each dimension. Then for the CW attack, the CW attack is unlike FGSM. This one optimizes over a change of variable. So this variable is going to be our adversarial sample. And this adversarial sample is going to minimize the distance between the adversarial sample and the truest sample so that in the case it's very similar to the truest sample, and then also the objective function. And this objective function is specifically for non-targeted attacks. The targeted attacks is slightly different, but it's same concept. There is a method to CW that you can test different values of K, which will tell you how, that could tell you how confident an adversary example is going to misclassify. We don't explore too much of that because we just use the basic minimum because we don't want to necessarily attack the agent using extremely strong parameters. We want to attack it using weak parameters to show that these agents are susceptible. So yeah, so you can apply direct CW attack to the basic DQN, again, because it's very close to normalized data. It's not the same for TensorTrade DQM, but instead we decided to change it slightly that we will instead will use X as a starting point and then apply apply an epsilon value or some scalar values from each dimension to all dimensions of X so that we have an adversarial example. Additionally, if you wanted to make this more complex, a little closer to CW, we could have included another bias, which would compensate for the value differences between the rounded down values of an adversarial to the true sample so that we can bound the estimated delta to be between 0 and 1, and that would still be valid. Then we have, this is the same idea I was going to mention before about whether or not we should normalize or not normalize this data. It is extremely difficult to do standard testing of k-values for C and W attacks on non-normalized data. You have an extremely large range of values, and they're not bounded, so it's hard. Then we have, because FGSM it starts from a starting point, right? We could necessarily provide human interpretable adversarial samples. When you have normalized data, it's bounded between 0 and 1. That may not be as easy to read than to read just technical indicators as a human would if they are overseeing this agent. So yeah, those, it makes adversarial attacking more difficult to evaluate, again, because it's non-bounded. If you bound it between 0 and 1, then you have technically a smaller region to test in. And ultimately, adversarials are dense for both normalized and non-normalized data, so it is better in the idea if you wanted for evaluation to bound it between a smaller range. So here are some more examples of the non-targeted FGSM and non-targeted CW attack samples to show you that these examples can be very adversarial even to humans. So you can see over here on this right side, there's the same picture from the same table from the before that we mentioned, that the dynamics of these attacks can look very similar to the original sample that it's using as a starting point or it's comparing to, but the actions can be very different. Here is the ratios, the failure counts and the attempt counts for attacks at any particular time step. And you can see that for the basic DQN, the attack success or the attack failure is much lower than for a more complicated DQN like TensorFlow and TensorTrade's DQN, which has a much larger action space. So here are some results that are showing you that the performance of a model at test time from using total reward is impacted by these attacks. And the bottom one is the difference between the control agent. So this control agent is for TensorTrade that's not under attack. Subtracted the difference between the performance at total reward at a time step compared to agents that are attacked at different chances. So chances at 1.0 would be every time SIP is attacked. Chances at 0.5 means that there's a 50-50 chance that a time step might be attacked. And you can see in both cases, and on these cases that we mentioned here, that the total reward performance, this test time evaluation, is impacted by these attacks. But what's more probably important to traders is that, are they losing money? What are their securities and external components being impacted? And we can see here that by impact that these agents, particularly TensorTrade, because TensorTrade is the only one with an external security, which is its portfolio network, is that it is impacted by the attacked agent. And we can see here that the agent for TensorTrade is losing money when it's attacked. But on the right side, we can see that it loses money, but also it impacts it in ways that we can't necessarily quantify, because that means that the reward function and the plot of the test time reward function performance doesn't necessarily mean that we know what's going to happen to the agent's external securities. Here we have the targeted FGSM and targeted CW attacks. Targeted, just as before, means that we are taking adversarial action that we specify. Here in this case, we're using for a Q value to a list of Q values for a particular state in all 3 actions. We pick the lowest Q value as the targeted action. And you can see here again that it's very easy to apply it to the basic DQN, but it's not as easily applicable without making a lot more assumptions and some more specific restraints for the more complicated DQN. And you can see that here we also have, again, the failure counts and the attempts accounts. It's very successful. It's very successful in attacking the basic DQN. It's not as successful for targeted attacks, attacking the more complicated TT DQN. But we also consider partial successes, which means that because the action space is so large, there are multiple actions that are of similar types. So there might be like 181 actions. So 180 actions are either buy or sell at different stock sizes. And so, yeah, so we consider a partial success when an action is the same action type as the adversarial action that we want to take. So if the adversary action is sell, we consider it a partial success if any action that is of a sell type is the changed action that from the perturbation. So again, we have some samples you can see here. It's just the show, but you already get the point. Here's the performance at test time for targeted FGSM. Again, basic DQN is extremely impacted by this. You can also see here by using the reward difference of the targeted and the control agent for TT's DQN. They are also impacted by targeted attacks and specifically the partial success attacks. Again, they impact the net worth of the agent, which is extremely important to people who have securities tied. Conclusion. So naive trading DRL agents are susceptible to test time non-targeted and targeted attacks resulting in compromise of external securities like portfolio or network. As we saw before, these parameters that we tested at were not necessarily strong. So that means that these agents are particularly weak and brittle to weak attacks in general. So yes, but so if you can consider what an adversary who's using more specified fine-tuned parameters that are more expensive, you can see that an agent would not be able to be robust nor resilient towards these attacks. So yeah, traders, if they're looking to deploy DRL agents, they should consider threat modeling like the threat model that we showed before and use adversarial training to defend against at least weak to moderately powerful attacks. So yeah, these are the references. Yes.
Excellent job, Nancy. That was a great presentation, and I've been waiting to see such a presentation since early 2018. So before we get into the questions, a little bit of a precursor. This work started with Ali Fathi, Dr. Ali Fathi at Royal Bank of Canada and myself back in 2018. We didn't have time to finish it, and then we finally found talented researchers like Nancy and Yasser, who's a PhD candidate in Portugal, to work on this. And we finally have our first draft, which is currently being edited for submission. Nancy, you've done a great job, as well as Yasser, who's not here. Thank you so very much. Now let's open the floor to questions. Does anybody have any questions they would like to ask at this point? Okay, I'm going to start. Nancy, what are the implications of your findings on the real world? Should algorithmic traders be worried?
Well, there was a reason why we use TensorTrade, and TensorTrade is at the moment a framework that is used for deploying real life, real world deep reinforcement learning trading agents. So that's the closest thing I can come to demonstrating that yes, the deployed agents in the actual real world are impacted by these kind of attacks.
Very well. Are these attacks practical in the real world?
So yes, these attacks are practical. Observational delay is extremely practical. It doesn't require an adversary to craft their own examples, but all they have to do is just intercept a previous few time steps and insert it at a future time. Those are extremely cheap, and because data in itself for time series it masks its own anomalies for if they're extremely close in time steps, it's very difficult to determine if a sample is adversarial or if it's just a mishap.
Very well. And most of your attacks, actually all of your attacks, are based on the assumption that the attacker has access to the internals of the model. Is that generally true? And if not, what should an attacker do to overcome that obstacle?
So it kind of depends. If the framework that these people are using to train their agents are open source. If they're open source, then all fair is love and war. So an adversary would have equal opportunity to use those to craft their own agents that are very similar to your agents, to their agents, such that they can be attacked using white box optimization methods. But if the framework is not open source, and it's much more difficult to necessarily use for optimization attacks like observational delay or denial of service are a lot more, are better implementation, are better in terms for adversary interference.
Okay, do you want to hint to your upcoming work as well?
So right now we're currently working on a paper demonstrating that given an agent, right, and there's a certain accessibility that this adversary has to this agent, that we could use information from this agent to train our own agent to steal its policy, one, or two, if you don't decide to just steal intellectual property, you could use it to perform adversarial attacks to make these adversarial attacks applicable and transferable to the target agent.
Very interesting. Since no one else is asking questions, I have to keep asking mine. What are your thoughts on potential defenses against these sort of attacks?
So I personally believe that you can't necessarily protect or defend all agents for all types of adversarial attacks, because it is just part of neural networks, which are extremely they're so complex that it would be infeasible to compute and to train an agent to be that adversarially resistant. However, there is a level of adversarial of resilience and robustness a model can be for weaker attacks as well as moderate attacks. So that is definitely something that traders or people who deploy deep RL agents should consider, because these models have to be robust to a degree of adversarial attacks and just noise variations.
Very well. Interesting. Now, before we end this presentation, does anybody have any other questions, comments, or thoughts they would like to raise about this research? If not, I'm going to ask you all to join in on a discussion. Is it ethical to publish this research? What are your thoughts? Nancy, would you like to go first?
Well, to be honest with you, I think it's ethical because we are showing that these agents are not robust and not resilient, so that people can be prepared for when they deploy deep RL agents. So that really is something to consider for any actual deployment, because like insurance, right? You have threat models and risk models, and those are important for actual deployments. And so that's the same thing is applied to these kind of intellectual properties.
Very well. Sai, do you have any thoughts on this? So Sai is saying if it's for a company specifically, it would be a requirement that they are warned beforehand. But if it's a general methodology or model, it would be ethical to just publish. And this is a common practice in vulnerability disclosure in the domain of cybersecurity. However, what if there are billions of lives and livelihoods dependent on this sort of methodology? How is this going to impact their livelihoods and their lives? Is this going to be a force for good or evil? We are essentially giving a tool to malicious agents or entities to enables them to disrupt the stock market. 80% of the trades every day are performed by algorithmic traders. Are we essentially disrupting 80% of the market? Milan, do you have any thoughts on that?
I think that's it's not about the 80%, but it's the information we find it and something is vulnerable. I think without considering anything, it is ethical to publish, because one thing we found something vulnerable, and that's what we try to avoid, right?
Well, that is a good argument,
Yeah.
but I don't know. Let's see. Sai says it can be ethical overall, but it can be dangerous for the individuals disclosing in terms of illegal action. So there have been instances of software vulnerabilities or hardware vulnerabilities being disclosed prior to informing the client community or the user community of a zero-day exploit, which have led to major attacks prior to the patch coming out. Now, that is definitely dangerous, and there are cases of companies or governments suing the disclosing individual over that particular disclosure or their particular disclosures. Now, the question is this problem patchable? Is it easy to change a few lines of code and fix this problem? The way I see it is there is a fire in the house, and there are two ways of putting it out. One, let everyone know that there's a danger, so they should be mindful and they should get out. And two, you should alert the authorities so that they can help out to contain the fire, prevent it from becoming a wildfire. This is why I believe disclosing or publishing this particular paper, these findings, is not only ethical, but it's ethically mandated. If we don't do this, there are other people who may find out about these vulnerabilities and use it without disclosing it, and this can turn into a wildfire. There will be a disruption in the market, there will be a disruption in algorithmic trading, but that disruption will stabilize much faster and at much lower cost than it typically would if it were to be undisclosed yet exploited. Does anybody have any other thoughts on this? Any other comments about the ethical aspects of this research? Nancy, how do you feel about this? Are you comfortable with publishing these results?
Oh, I am. I mean, to be honest with you, with this whole topic, right? If I'm not the one publishing this topic, right, then there's going to be obviously the point of this whole paper is to mitigate and prepare people who are deploying these agents so that they can be prepared for these perturbations and kind of types of attacks. And yeah, without some sort of guideline or paper publication that these things exist, some people just will ignore it, or it will not gain traction in for when actual deployment happens, that this is of concern, because then it's just an idea and it's not an actual written researched area.
I agree with you. And Sai brings up a good point. Who else has done this research but Nancy? We don't really know, which means the bad actors could be circulating this information without it being in the light, and the boom. And then boom, big problems. And I agree with Sai. So let us move forward with full speed. I'm going to finish editing the paper, hopefully by this evening. It needed a little more edit than I expected. And we will put the preprint on archive by Monday. And we'll see what happens. Nancy, once again, thank you so very much. I'm going to stop the recording now.